Ladies and gentlemen and fellow researchers, my name is Tana Zarzati from Electrical Engineering Department of 10 November Institute of Technology, Surabaya, and it's a pleasure to present my research entitled Voltage Stability Enhancements using NCPI-Based Optimal Reactive Power Compensation under Critical Line Outage. To begin, I will provide an overview of this presentation structure to guide the flow of this discussion. Now, let me walk you through the structure of these presentations, which is organized into 5 main sections: introductions, voltage stability index, North Sulawesi system, simulation and results, and the last one is conclusion. So the first one is introductions. Let me start with the background of this research. As electricity demand rises, many power systems now operate near their stability limits, making them more prone to disturbance. In 2024, a single line outage caused a major blackout in North Sulawesi and Gorontalo system, leading to a 33 megawatt load loss. This highlights the serious risk of voltage instability during NMIN1 contingency. To address this issue, the study proposed using static var compensator for reactive power support to improve voltage stability, especially during line outage and heavy load. The main contribution of this study is the application of the novel collapse prediction index to improve voltage stability by determining the optimal sizing and location of SVC. So the next one is to evaluate voltage stability. Various index have been developed. In these sections, a brief comparison is presented between 3 line-based voltage stability index, which is FSE, NCPI, and LKP. FSE have been developed in 2002. It's used to estimate how close a line is to voltage collapse and is often applied in real-time monitoring. This slide also represents the FSE equation, whose values typically range from 0 to 1, and a line is considered unstable when the value exceeds 1. On the other hand, LKP introduced earlier gives a quick estimate of voltage stability based on line parameter and is mainly used in steady-state planning. Same with FSE, LKP value typically range from 0 to 1, and a line is considered unstable when the value exceeds 1. So this slide compares 3 voltage stability index, FSE, LKP, and NCPI. FSE has several limitations. It ignores active power, power flow direction, and line resistance, making it less accurate under high apparent power loading and high active power loading. LKP includes active power, but still neglects power directions and resistance, leading to error under stress condition. NCPI solved this issue by considering all key factors, which is voltage angle, active and reactive power, power flow directions, and resistance, making it more accurate and reliable for predicting voltage collapse. So what is NCPI? NCPI is a line-based voltage stability index designed to measure how close a transmission line is to collapse. Unlike FSE and LKP, it includes active power, line resistance, and power flow directions, making it more accurate, especially during system stress. NCPI values range from 0 to above 1, with values above 1 indicating instability. It's also useful for guiding the best location and sizing for reactive power compensation like SVC. To evaluate the performance of the proposed method, this study applies it to a real-world case, the North Sulawesi and Gorontalo power system in Indonesia. The North Sulawesi system includes 48 generator and 54 load and operates through 82 transmission line. These sections present 4 scenario simulation. The first one is the NMIN1 contingency analysis. In this scenario, a total of 82 single-line outage cases were simulated. For each outage, 3 voltage stability index, which is NCPI, FSE, and LKP, were evaluated to identify the most critical transmission line. As shown in the table in this slide, the Tanjung Karang Isimu line consistently record the highest LVSE value, indicating it is the most critical and vulnerable line in this network. In this particular NMIN1 contingency cases, the disconnection of the Tanjung Karang Isimu transmission line result the highest line voltage stability index value across all of the outage scenario. As shown in the system topology on this slide, the Tanjung Karang Isimu line serves as a heavily load backbone, playing a critical role in supplying power from the Isimu area to the Batu Pigo region. This is primarily due to the line's function as a major transmission path, handling significant power flow. When this line is disconnected, the parallel line, which is Tanjung Karang Anggrek, are forced to absorb the redistribute load. This results in a substantial increasing in loading, which reach up to 52% and causes a voltage drop about 3%. The Tanjung Karang Isimu line outage pose the highest risk, confirming it is as the most critical sources of voltage stability in this system. So the second scenario is heavy apparent power loading. In this scenario, both active and reactive power were increased simultaneously at each bus. As shown in the table, the NCPI successfully identified the weakest location in this network. The Tanjung Karang Isimu transmission line recorded a value of 1.21, exceeding the NCPI threshold. This indicates that the Isimu bus is the most vulnerable point in the system under this loading scenario. Because of its persistent instability, the Isimu buses is also identified as the most appropriate location for placing the static fire compensator. So this chart represents a comparison of NCPI, FSC, and LKP under having apparent power loading condition. As shown, the NCPI consistently yields higher value than both FSC and LKP for the Tanjung Karang Isimu line. This indicates that the NCPI is more sensitive to change in the system and more effective in highlighting potential instability. So the third scenario is the worst case condition in the system where the most critical transmission line, which is Tanjung Karang Isimu, is disconnected and the load in the Gorontalo area is increased to 1.3 times its nominal value. Under these combined stress conditions, a voltage collapse occurs, with the minimum bus voltage dropping to 8.1 per unit. This indicates the system was unable to supply sufficient reactive power to maintain voltage stability. In terms of index performances, NCPI identified the Anggrek Isimu line is the most unstable, with a critical value of 1.14, effectively capturing the risk of voltage instability. On the other hand, FSC and LKP failed to reflect the criticality of this line, yielding a lower value of 0.72 and 0.84 respectively. This confirms that NCPI provides more reliable assessment. So this graph compares NCPI, FSC, and LKP under the worst case scenario. Only NCPI crossed the critical threshold of 1, clearly identify Anggrek Isimu as the most unstable line, aligned with its high loading, about 97%, and significant voltage drop, about 6%. In contrast, FSC and LKP remain below 1 and fail to capture the actual risk, with FSC misidentifying Tanjung Karang Anggrek as the most critical lines. So the last scenario is reactive power compensation sizing and location. After the Tanjung Karang Isimu outage and load increase, the system experienced voltage collapse. To recover, an SVC was installed at Isimu buses and various capacity ranging from 50 to 65 MVAR were tested. The results show that the voltage improved to more than 0.97 per unit, with 65 MVAR offering the best stability. NCPI respond most significantly, dropping to 0.67, proving more reliable than FSC and LKP for guiding SVC sizing under critical stress. To validate the SVC optimal location and capacity, NCPI value were compared for normal and min1 contingency and post-SVC condition. During contingency with load increase, NCPI exceeds this critical threshold, which is 1, indicating instability. After installing a 65 MVAR SVC at Isimu buses, all NCPI value dropped below 1, restoring the stability of the system. Average NCPI fell from 0.23 to 0.12, decreased about 44%, and the maximum from 1.14 to 0.7 decrease about 41%. This confirms that the proper SVC placement and sizing can significantly reduce system instability under stress. So this is the impact SVC compensation on the voltage profile buses in the system. As shown in the chart, it's telling a 65 MVAR SVC at Isimu buses raised the minimum voltage from 0.81 to 0.97 per unit, increase about 20%. The average from 0.88 to 0.99, increase about 12%, and the maximum from 1 per unit to 1.3 per unit, increase about 3%. This result confirmed that the SVC placement significantly improved voltage stability and that NCPI decreases as voltage stability increases. Following the simulation and analysis, the key conclusions are summarized as follows. It can be concluded that this study successfully applies the NCPI to identify critical line under N-1 and load increase scenario. Compared to FASC and LKP, NCPI offers higher accuracy by considering key parameters like active power, reactive power, voltage impedance, and power flow directions. Using NCPI, a 65 MFAR SVCU was optimally placed at ISIMU bases, increasing voltage profile about 20% and reducing NCPI by 40%. This confirms the NCPI-based approach effectively enhances voltage stability under stress condition. So thank you for watching these presentations. If you have any question, feel free to reach out via email or LinkedIn. I'd be happy to connect and discuss further. Thank you.